Yes, so we're trying to understand like small neural nets, and because here's kind of my thing, and it, this it's like an observation, but it's like let's say you're trying to train like Dolly or something, and so you have like a transformer architecture, or like it doesn't matter. Like, let's just say you're doing image classification. Like at some point, your input data is being mapped. I mean, you can interpret it in this way. Like it's not necessarily you should interpret it in this way, but your input data, like an image, is being mapped to some point, like an R 1,000 or something, like some high dimensional space, and then like you're wanting your like so if you're just doing like image classification, you're wanting the neural net to map that point in high dimensional space to like some other point in high dimensional space, such as like a lower dimensional space, but still pretty high dimensional. So like a like a categorization, like a one hot vector, or like a probability distribution over a bunch of categories, a bunch of possible image categories, and so the thing is, it's kind of like, so it's like neural nets can, like, empirically they can like fit your training data, because like at the end of the day, your training data is like all these images, which are these points in high dimensions, paired with like the output, which is another point in high dimension. And so like neural nets can like using like some form of gradient descent can like learn these associative pairings, which is weird. um, I mean, it's like some form of I mean, it's kind of like solving systems of linear equations, except they're non-linear because you have like tan h's or something. But anyway, the other point is that, okay, so like the first point is like it can solve those problems. Like you can give it like a big system of these input-output pairs, and then it can learn to map each input to the target output in the training set. But then the other weird thing is that like it generalizes. So like if you give it like an input that's like somehow from the same distribution, it will like categorize it correctly. And so if we take all that down to the two-dimensional case, right? Like it would be like, okay, this point is like an input point, and we want to map it to this output point. Here we're doing R2 to R2, and then like this is another input point, and we want to map it to another output point. And so anyway, the weird thing is that like the generalization would be like, this point over here is also from this same distribution as the input points. And then like when the neural net like happens to when it fits the training, like it moves around all the points. So like here's like point 44, and then it's like the way it moved it around like corresponds to how humans do image classification. So that's weird. But anyway, like what we're doing is we're we're dealing with like the first problem of I guess like trying to find like training sets that neural nets like can actually memorize or like learn. So like in this case, like the way I have the visualization is we have lines between, because the input and the output are the same, like R2. So we have lines between input and output points in the training set, and each pair is a different color. And So like, this is layer 1, this is layer 2, and the target output stays fixed because like it's fixed, and then like where the neural net is mapping the particular input, like changes, and then like in the output, in this case, it's mapping each input point to its target output point, so like it correctly learned the training set. And also so we were trying to like we're trying to understand like when the neural net like cannot fit a training set, because empirically there are size 3 training sets that it can't fit, and that has something like where the neural net right now is linear, so it's literally solving a system of linear equations. And but I guess like I was trying to like develop like is there like a visual intuition for when, or like is there a property of a training set of size 3 for when the linear neural net like cannot fit it? And this is quite possibly like a fool's errand, but that's literally what I'm doing. So I'm gonna do that for like the next 20 or 30 minutes. So so one thing we're like confident about is that there is no, well, we're kind of confident. We're not like 100% confident. But we believe like there is no training set of size 2 that the neural net cannot fit. Yeah, like I was trying to remember like, because it's something like, it's like if you have a system of linear equations, then it's like each equation represents, I think I want to say like if you have an equation within unknown variables, then that represents like an n-1 dimensional hyperplane in Rn. So it's like a volume. And so the solution, if it exists, is each equation represents a volume, and then the intersection of all of those volumes is going to be the solution space. And it's kind of like, in our case, the unknowns are the weights and the biases. And so if we just have a single layer, right? You have, I believe it's you would have 2 weights per output unit, and then each output unit would also have a bias. So you have 6 unknown variables. So like each input output in the training set is a equation, is a linear equation, and the solution space would be a 5-dimensional volume. And so actually it kind of seems like there should actually be, because if you have 2 5-dimensional volume, like if you have a training set of size 2, then you have 2 5-dimensional volumes, like an R6. And I think just saying you have, like, I don't think it's guaranteed that 2 5-dimensional volumes in R6 like have to intersect. right? Like I think you can have two five-dimensional volumes in R6 that don't intersect, isn't it? Um, but yeah, like we're trying to map like that from like the geometry of like systems of linear equations to like what I'm looking at on the screen. So like like should I not be able to like construct a training set either of size 2 or of size 3? Because also like empirically, when we move to like training sets of size 4, like almost all of them are not solvable. Right, let's just look at that. And then also empirically, if you look at training sets of size 3, like most of them are solvable, but there are some that are not solvable. Okay, so like this is a training set of size 4, and it's like this guy has to map down to here, and I can't see the blue, but it goes some way. The red guy, this guy has to map down here, this guy has to map up here. Okay, so we're gonna run our optimizer, which is Atom, which is Adagrad with, is it Adagrad? No, it's adaptive momentum. No, I like, like I don't really understand the optimizer I'm using, and that's fine. Okay, so, okay, now, humorously, it kind of managed to fit this particular training set. Right? I mean, almost. Like, there's a little discrepancy with the blue. But, okay, so let's look at a different size 4 training set. This is a different one. Yeah, okay, so like it can't fit this one. And what it likes to do is put all the input points like on a line running between the target points. Yeah, I think because visually, like the only thing, whoops, I'm breaking the only thing like a two-dimensional linear transform can do, right, is like it can rotate the input grid, and like it can flip it, and like it can shear it. So it seems so since the things that the neural net can do to the input grid are like very limited, it seems like you should be able to like just come up with like a training set of possibly size 2 or size 3 that is unfittable. But yeah, like I kind of because I thought training sets of size 2 were always fittable, but then I just did that line of reasoning where it's like, well, they're volumes in R6 of 5 dimensions, so I mean, like by analogy, like so there should be like volumes in R6 that have zero intersection. But they'd have to be like parallel to each other. So I mean, it's possible like you might not be able to represent that case like on this thing. But it also seems so like another conjecture would be like if you start with a training set of size 2, like that is fittable, you should be able to find like a third training point that you could not fit given the first two. Um, yeah, so we'll look at that idea. So we'll just do like, okay, training set is size 2. Oh, that's weird. Like, what's the probability of that happening? I don't know. But I also think it would be easier visually if, I mean, there's kind of two problems. Like, one problem is like we have 2 layers here, which, since I'm doing like linear, since everything's linear, like it's mathematically equivalent to have only 1 layer, because all linear transforms compose to form other linear transforms. But maybe if I initialize the neural net so that it's the identity function, then maybe we could see like this sequence. But then it's also like, I wonder if it's guaranteed. Yeah, let's just do that. Okay, so we're gonna initialize the neural net so that it's the identity function, so that at the first step, like we are right here, like it's gonna be the same grid, like, because it's the identity function. How easy would that be to implement? I feel like not very easy. Can I just add that? Kernel initializer. Yeah, they call the weights the kernel. I don't know why. Kernel initializer zeros. Yeah, but I don't want zeros. I want, can I say identity? Like, is that cool? Oh, dang. But is that gonna work? That's the question. It might work, or like I'm using GitHub Copilot, so it possibly just made that up. We don't know, but we're gonna find out right now. Yeah, yeah, I don't think it liked that. Is it giving me an error? It's not giving me an error. Oh, do I need weight initializer also? Okay, we're gonna have to put all these on their own line. Okay, this one, and then this one. Okay, so then do I need weight or bias initializer? I should really just go out to the website, but yeah, actually you do want zeros for the bias if you're doing identity, isn't it? Oh, why did it do that? Don't do that. What are you? Oh my god. Okay, comma. There you go. I'm gonna get identities. Oh. Why is that? Okay, so I'm thinking like that doesn't actually. Okay, so we have to go to like Kara's, I don't know, weight initialization, and I want it to be the identity function, kernel initializer, bias initializer. Yeah. Available initializers. Zeros, ones, identity. That's the one. And generates the identity matrix. Okay, so you can't just use a string, you have to use this, I guess. Okay. Although I'm using JavaScript, so like it may or may not. Yeah, I should probably, well, I don't know. I'll just try that. So tf dot init. Yeah, I don't. Okay, I'm gonna have to look at the JavaScript. TensorFlow JavaScript, like API. Like I need the API. And yeah. Okay, then we need initializers. Oh yeah. Oh, there it is. Only gain. So do I just type in that? Like as a function? Initializers identity. Does it like that? Oh no, it doesn't like it. It broke. Oh, you have to supply gain? Like explicitly? So like 1? I would like a gain of 1. 0.0. Just okay, this is not working. Why would that not be working? The bias would be 0. And wait, where's the thing? TF initializers identity 1.0. Array sync, like, well, how do you use this? Can you use it standalone, or like do you just pass it? Oh, I see. I don't understand why that doesn't work. Okay, let's print the weights. Yeah, let's print the weights. So like layer 1, is that gonna, no. Why would that not be accessible? in layers. I think you can just say wait. Array sync. Get weights. Why not? Why not? Okay, get weights. Okay, I'm gonna abandon ship on this. Like, we're just... I don't know why that's not working, but, so... Okay, we'll just go back to everything's standard. Alright. Okay, so I think like, okay, so we're just gonna look at, you know, I think like we're gonna try to understand visually how the neural net will probably like say solve this. Particular like size 2 training set. And then it seems like maybe you could then generate like a third training point that it can't fit given the first two. That's like the theory. So you know, for this one, I mean, it just seems like you like flip it that like both ways, and then you do like some scaling or something. So what did it actually do? I think it just, yeah, it just rotated it. Is that what it did? Because 90, 91. Yeah, it just rotated it. And then shrunk it. So but does it always find the same solution? Yeah, not necessarily. So okay, so it seems like you could say something like, so for instance, like the 1 is typically being mapped. Yeah, that seems like a thing you could do. You could just say like, okay, over all the various solutions, the 1 is kind of being mapped over here. So what if you say like, the 1 has to be mapped like down here? Would it be able to do that? Okay, so we're gonna try that. So I have to, so this is the training set as it currently exists. And So I'm going to manually type in the training set. Those are the input points referenced by index. And those are the corresponding output points referenced by index. So let's just confirm it's the same thing. Good, good. And so what we're saying is like, hey, of course, I mean, you know, okay, so like the 1 is typically like up here or down here. What if we say like we want the 1 to map to itself? So that means the 1, which is typically being mapped in this region, like we want it to be mapped up here. Is that going to break everything or not? Okay, so like we're saying the 1 has to map to itself. I mean, looking at this, it kind of looks like it's going to easily do it, but yeah. Okay, so what if we like try to map the 1 down here? So say like we want the 1 to go to like 90. Yeah, I'm thinking that looks like it's going to easily fit also. I guess another thing you could say like, okay, the 97 is always close. So what if we try to put the 97 far away? Like what if we try to put the 97 down here? Try that out. Yeah, no, that it can easily do that. It has to scale it like crazy, but it can easily do, whoa, it can easily do that. I don't know, put the 97 at 0. Right? It's like a triangle. But it looks solvable. Yeah. Easily solvable. Put it at 6. I don't know. 97 goes to 6. Okay. It's like we have all sorts of crazy crosses. Easily solvable. Okay, great. Well, okay, what if you do something like this guy has to go all the way over here, but then like something over here just stays, right? Yeah, let's look at that. Let's look at that. Okay, so we want, say like 99 to go to 0. But then we want, say, like 1, you know, to stay in the area. 1 go to 2. Okay, see if I can fit that. And then let's like try it multiple times. So it seems like if you then like, it kind of seems like if you take one of the middle points and then say they have to go to 9, that seems like it would mess it up. 54 goes to 9. Okay. Okay, it can inexplicably solve that. Okay, what if we say 9, you know, has to go down? What if we just say 9 goes to 99? 9 goes to 99. Right, because like these two want to put it in here, but then this one is like, no, you have to go all the way down here. Oh, it can easily do it. I mean, it seems like it can fit like any any size 3 training set, but I know it can't, because if you randomly generate 3-dimensional training sets, every now and then it finds one that it can't fully fit. But also empirically, those are like very sensitive. Like if you move, you know, like if you change one of the training points by a very small amount, it becomes solvable. Okay, okay, here's an idea. What if we do like a shrinkening, right? So so we say like 9 has to go to 46, and 90 has to go to 63. Okay, so 9 has to go to 46, and I forgot what 90 has to go to, I think I said 40, no, damn it, 63? Yeah, 63, okay. And, right, so this is a great shrinkening. Well, that didn't do what I thought it would do, but yeah, okay. We'll see, I thought it would put like the entire grid in between. Yeah, kind of like that. And then we have a point that violates this. So we take like the middle point and say like, yeah, nah, that doesn't seem like it's going to do anything. What if you just do the opposite? You say like 45 has to go to 8. Right? So 45 is going up to 8. And... oh, I think we found one. I think we found one. It's not solvable. Let me do different weight initializations. It's not solvable. Do another weight initialization. I can't solve it. Oh, dudes. 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 That is excellent. That is excellent. I don't quite know why I can't solve it. It's just this idea of like, you have two training points that want to like shrink the grid, but then this training point like counter is the opposite of that. Like it wants to not shrink the grid. So then the linear transform is like, no. Because like if we switch the activations to tanh, it should be able to solve it. Yeah, because like it has to pull that corner down. That was crazy. Did you see it pull the corner down? Look at this corner pull. It's like, screw you, I'm pulling the corner, I'm non-linear. Look at that corner pull. Oh my word. Oh my goodness. But like with linear, it can't do that. Can't pull the corner. Whoops. Can't pull the corner. Okay, so I don't understand like generally, because the whole intuition for this was like, two of the training sets it wants to shrink it in the middle, two of the training pairs. It wants to compress the grid, and then you have like one training pair that's opposite of that. So I don't know if that like how well that generalizes, nor also if that's like exhaustive in terms of, I mean, it might not be possible to characterize because, like again, at the end of the day, you're like, you have each training pair is a linear equation with 5 unknowns, 6 unknowns, 4 weights and 2 biases. And so each linear equation represents a 6 minus 1 5-dimensional volume, and so we have 3 of these volumes if you have 3 training pairs, and so there's going to be no solution whenever those 3 volumes do not all intersect at one point. Or, well, it doesn't have to be one point. I guess it could be a volume of points. But, I mean, I guess it's possible that never happens. I mean, it's also not... we're not entirely clear that this doesn't have a solution. Like, it just... Atom doesn't appear to be able to solve it. But anyway, like, we made some progress here, right? Because we have like training sets. Like, this is a training set that we developed an intuition that produces a training set that empirically is not solved. So that's a pretty good live stream, if you ask me.